Mole relationships.
Yeah.
Okay, so we kind of skipped the first one because it looked the same as the other one, but it actually had a different number of moles. I don't think anybody actually did it, but if you did, the answer was minus 12.
I did not.
Good job.
Yes, I did. I got 12.
Gold stars.
I did.
The answer to problem number 1 is 12.
Oh no, I did not do. I don't.
Well, the example started with 2.4 moles of hydrogen sulfide, and problem number 1 started with 8 moles of hydrogen sulfide. So it was actually a different problem. Okay. It was invisible. Okay. The next one says ammonia, NH3, that's used for fertilizer, is made by causing hydrogen and nitrogen to react at high temperature and pressure. How many moles of ammonia can be made from 0.15 moles of nitrogen gas? So the first thing that we need to do is write a balanced equation for this. You may remember that hydrogen and nitrogen both are diatomic gases. So we're going to need to start our equation, and I kind of spread the equation out just so I have lots of space in my BCA chart. We're going to have H2 plus N2 yields NH3. And the first thing that we need to do is balance this. So one thing that you can notice about this to balance it kind of quickly is that for every 1 nitrogen, we're going to have 3 hydrogens. So if we've got 1 nitrogen here, we're going to need 3 hydrogens. And then what we're going to produce is 2 moles of ammonia at that ratio. So that's the first part. That's the equation part. Any questions so far? You guys feel okay about equations? We can balance stuff. Yeah. Ta-da. Sorry about that. I appreciate you guys telling me that I can't, because I just don't look behind me sometimes. Okay. Now what we're told is that we're going to start with 0.15 moles of nitrogen gas. So in my before line, I'm going to put 0.15 moles. It's asking us how many moles of ammonia can we make. So it's not.
It literally says freeze.
But it's not supposed to be. Dang it. Okay. In my defense, I have to record it, and I have to present it, and I have to send it to the projector, and then the projector has to actually do its job. It's like 4 things. Okay. I just needed to read my mind. So it asks us how many moles can be made from moles of nitrogen gas. If we're starting with 0 moles over here, and it's here's 0.15 moles. The abbreviation for mole, M-O-L-E, is mole, M-O-L, which if it saves you time and you like using it, whatever, you can use it. By the time we do MOL, I usually just throw the E. So we're trying to find how much we make in this reaction. Now, what that means for those of you who don't like to do extra things is that you don't even have to really think about what should go in this part of this chart because we don't care.
I feel like that's important.
I mean, we can fill it in. It's pretty easy, but there's a couple of different ways you can approach this. Since we're still working on understanding how to do it, I'm going to show you the longer way, and then I'll show you the shorter way. Does it ever happen to you guys in math class? Your teacher goes through weeks of showing you the long way and then shows you the trick to do it really fast. I just don't, no comments. Okay. Yeah, that's what happens when you learn limits in calculus and then they show you how to do an integral really quickly. Anyway, so if we start with 0.15 moles of something, I'm going to draw a line here, and this is going to be my like math part of the paper. So I've got 0.15 moles of N2, but I want to know how much ammonia I'm going to get. I know that for every mole of nitrogen gas I start with, I'm going to have 2 moles of ammonia that I produce. So I'm going to have 2 moles of, I need more space, 2 moles of ammonia for every 1 mole of nitrogen. That's all that this means. This is just a ratio of the things just based on the equation. So when I do that, I'm going to do 0.15 times 2 divided by 1, which is going to give me 0.30. My units, my moles of nitrogen are going to cancel, and I'm going to be left with moles of ammonia. So that answer should go here. So I've solved it. Yay. Okay, those of you who like to fill in the whole thing. Yes.
Well, I finished the rest of the packet.
Cool. Show it to me afterwards.
Okay.
Okay, so if we are going to use all of those and we want to know how much of each of these we have at the end, here we're going to start with 0. We're going to add 0.3 moles. We're going to end up with 0.3 moles of ammonia. If we use all 0.15 moles of nitrogen, we're going to end up with 0 moles of ammonia. And then, those of you who like to complete things, the easy way to do this, I could write out all the math for it, or I could say, okay, for every one of these, for every 1 nitrogen, I'm going to end up with 2 ammonia, and I'm going to need 3 hydrogen. If this is a 1 to 3 ratio, I just have to multiply the number of moles times 3 to figure out how much I needed to react it with. So then over here, I'm going to start with 0.45 moles of hydrogen gas. I'm going to use 0.45 moles of hydrogen gas. I'm going to end up with nothing, 0 moles. That's the easy way to do it. Because if I understand these are relationships about ratios, if this nitrogen is 1, and I'm looking at a 1 to 2 ratio of nitrogen to ammonia, then I know that I just have to double the number of moles of nitrogen to figure out how much ammonia I was going to use. All right, what questions do you guys have about number 3? Any questions? Okay. The poison gas, phosgene, COCl2, reacts with water in the lungs to form hydrochloric acid and carbon dioxide. That sounds terrible. How many moles of hydrochloric acid would be formed by blah, blah, blah? So the first thing we need to do is write our equation.
I just yawned. I wasn't sighing. I was yawning.
So we've got our COCl2. It's reacting with water, H2O, in the lungs to form hydrochloric acid, HCl, and carbon dioxide, CO2. So if we've got 2 chlorines here, we know we're going to need at least a 2 here. And 2 there. Does this just work like that? 2, 2, 1. And it's just ones. 1, 1, 1. Yeah, so you can, like least common multiple it, and that's fine. Some people did that on the test too, but I mean, it's still balanced. It's just harder than it needs to be. All right, so we're told how many moles of hydrochloric acid would be formed by 0.835 moles of phosgene. So we're going to use 0.835 moles of phosgene. See this 1? You see the 1? The 1. So if I'm going to do this the easy way, 1, 1, 1. So it starts with 0, right? 0. I'm going to make, 0.835 moles of CO2. I'm going to use this. But this is a 2. So if this is a 1 to 2 ratio, I'm going to have twice as many moles. So I have to multiply that times 2. 0.835 times 2 is 1.67. If you want to do this the long way, 0.835 moles of phosgene times 2 moles of hydrochloric acid for every 1 mole of phosgene. It's going to give us 1.67 moles hydrochloric acid. You okay, Hayden?
Mhm.
You're just like giving me like this dead stare. I'm so sorry. Any questions about number 4?
No.
You guys feel better about this today than you did yesterday?
A little.
Yeah.
Neato, because you guys had 7th period completely freaked out. This is the hardest day of chemistry ever. I was like, where did you hear that? It's what 2nd period told us. It's like, it's not. Ah! Anyway.
Yeah.
Yeah.
So, so like for the other ones, where you have like zero, like for the last one, you have 0.835 moles for the oxygen. Like, because it doesn't tell you how many moles, you just assume it's the same.
What do you mean? Oh, I'm just assuming I used all of it.
Okay.
Yeah.
So you do that for every problem.
I mean, they will get more complicated and they'll tell you. But what we're doing here is we're saying, okay, we're going to use it all so that afterwards we have none of this left. We've got none of this left. We've produced 1.67 moles of this, and now we have 0.835 moles of carbon dioxide. So like different problems will ask you for different things, and sometimes what you have left over is going to be like what's left after a reaction happened because you had too much of something. So instead of subtracting it from, excess or infinity amount of oxygen, like you'll have a limited amount and subtract it. It'll make more sense when we get there. This is just baby steps. Okay, number 5. Number 5, they didn't even give us a PCA chart. Like what? Iron, metal, and oxygen combine to form the magnetic oxide of iron, Fe3O4. How many moles of iron can be converted to magnetite by 8.8 moles of pure oxygen? Make your BCA table. Yeah, okay.
Oh, I did not.
It's like right there on the instructions.
I kind of skipped over that part as soon as I got
It was
to
in
it.
front of
Honestly,
you,
it's
so
very
it
easy.
was visible.
As soon as I had all the information I needed, I just skipped it.
Sometimes when I give instructions on tests, I like to number the instructions so that it looks like a question. Because then people read it. Okay, so we've got iron metal, so that's just Fe, and oxygen, which is a diatomic gas, O2, combined yields to form Fe3O4.
Oh, I did not do that.
How did you not do that?
Whoa, I did not ask for the 2.
Well, I didn't. I told the whole class they didn't do it right.
Okay, so there's our balanced equation. How many moles of iron can be converted to magnetite? Okay, so this is more complicated, guys. We're given our moles of oxygen, which is 8.8. All right. How many moles of iron can be converted to magnetite by 8.8 moles of pure oxygen? So we need to know how many moles of this do we need to produce this, right? Do we know how much iron oxide we're making? Does it tell us? It doesn't tell us. So we just have to figure out what this ratio is. How many moles of iron we need for 8.8 moles of oxygen. Anybody know like now? Yeah.
Yay.
Did you do it in your head or did you do it with math?
Well, Milo just asked me, and then I did it, so I got it.
Oh, okay. So you could do this in your head, right? Because you need 2 parts oxygen for 3 parts
I
iron.
did it in my
So 1 part would be 4.4, and then you have to multiply that times 3. So that's the fast way to do it. The way that it looks written out would be, yeah, 8.8 mole of oxygen, and then you need 3 moles of iron for every 2 moles of oxygen, which gives you 13.2 mole. How much iron oxide will that give you? 4.4. The easy way to know is if this is a 2-to-1 ratio, you're going to have half as many moles of iron oxide as you did of oxygen. So this first one, How many moles of iron? It's going to be this one. How many moles of iron oxide will be produced? 4.4. Any questions? Coca-Cola. The recipe for Coca-Cola Classic is a closely guarded secret. Researchers outside the company believe the flavoring mixture known as 7X contains oils of orange, lemon, nutmeg, cinnamon, and coriander. Which, to be honest at this point, okay, you guys see this list, which also, the original mixture also contained caffeine, vanilla, caramel, lime juice, sugar. Like, think about how many of the special flavors there are of Coca-Cola and how many of them are already listed here.
They just stuff it full of
Vanilla, lime. There was a cinnamon one. There was lemon and there was orange.
That also
There's a lime Coca-Cola.
Vanilla Coca-Cola is amazing.
Vanilla Coca-Cola and then the cherry.
Vanilla cherry.
So good.
Okay. Over the years, the recipe has changed. For example, the original recipe contained citric acid. You know what citric acid is? Blah, blah, blah. Citric acid. The purest way you can eat citric acid, by the way, is that's the powder that's on Sour Patch Kids.
Isn't it colored together too?
Yes, citric acid.
One time, my sister gave me a spoon of citric acid instead of sugar, and I took a bite of it.
I'm so sorry.
It burned my mouth.
Did it?
Yeah.
I'm so sorry. I'm glad you're okay. But this was combined. But this was, look at this. Now we don't have citric acid, which is something that comes out of, guess what? Citrus fruits, orange, and lemons and stuff. But this is now combined with phosphoric acid to cut production costs.
Capitalism.
Corn syrup replaced sugar for the same reason. All right. So we have this situation here where like all my labels got shifted.
Yeah, I know that confused me, and I was like, did I do this wrong?
So sorry.
Yeah, I had to do
There we
that.
go. Okay.
Every single one. Do it for caffeine.
Yeah.
To produce 1,000 cans of Coca-Cola Classic, 40 grams of caffeine are reacted with phosphoric acid and other ingredients. How many moles of phosphoric acid are required? Okay, we're going to not hurt ourselves. The fastest way to do that is to say, okay, caffeine is going to be, this one's going to be 0.21 moles, right? And it's asking us about phosphoric acid. So this has a coefficient of 1. Phosphoric acid has a coefficient of 4. So the number of moles of phosphoric acid in a 1-to-4 ratio, if it's 1 to 4, then it's 0.21 to 0.84. This is like, you guys remember in like English class when you would do things with the colons? You know, so this is like saying like 1 to 2 is the same as
Those are so easy.
0.21 to 0.84.
Those are so easy.
Those of you who prefer language arts, that's how you can do
Everybody
these.
lost their minds over it.
I
I
know.
remember that. It's like, oh wait, like the dice compared to that.
Yeah.
Yeah. Those are stupid.
I'm just writing caffeine there.
Yeah, I think I
The thing that I don't like about Facebook is, so like, what? I know, there's a segue here. Because you guys were talking about an old teacher, right?
Oh.
I know. It doesn't make any sense. So I've reached a point in my life, like, you know, I was in elementary school a million years ago, like 30 years ago. So not only have all of my teachers that I had in elementary school retired, they're like dying. And so like I'm like just encountering them on Facebook again, like just in time to see like, oh, so and so just died yesterday. And I'm like, dang it. Because I remember them as being like 30 years old, which is younger than I am now. Oh, okay. Anyway, it's kind of trippy. I know, she's like having a great time over there. All right, how many moles of carbon dioxide are required? If I've got 0.21 moles of caffeine, my carbon dioxide here is 6 times as much, so I need 6 moles of CO2. for every 1 mole of caffeine. Need to multiply it by 6, which is hard to do in my head. So it's 1.2.
1.26.
So 1.26. Okay. You guys have any questions about any of those?
No.
I got it wrong because I thought it's like where you put the arrows. I thought caffeine was the
Yeah.
second one.
Yeah, the
I'm
only
sorry.
reason I knew that is because I knew CO2 was not.
So you guys will figure it out.
Wow.
You
I'm
only
super
I didn't know that
smart.
one.
I'm not that smart. That's weird.
I didn't either.
Okay, so what we're going to do tomorrow, because you guys have some time here, is work on this worksheet number 2. We can't do the lab from home.
Oh, I forgot it's Wednesday.
It's Wednesday. Okay, so a lot of this looks this. You guys are like falling apart all of a sudden. All right, so the instructions say write the balanced chemical equation. We know how to do that. Identify the given with units and what you want to find with units. Show your setup with units, and then it has stuff like check sig figs.
That
That
was like
test,
my
I got
least
like a-
favorite part of like all of
I got like a
chemistry.
70 on that test.
Yeah,
Just for the
yeah.
sake of-
I got like a 44. I hated
That's
that.
why we only like do it once.
Well, it's the second time.
It's fine. This is fine.
Unit 1.
Okay, so you guys understand the idea of percent, right?
Yes.
Good. Okay. So we understand percents. Here's the special equation you guys are going to need. At least I'm giving it to you.
We have to memorize.
Yes. Percent yield. So if we want to understand percent yield, what we want to know is how much we got compared to how much we expected to get. So it's going to be our actual yield divided by our theoretical yield times 100% because percentages. Okay, so everybody have that actual yield divided by theoretical yield. All right, so the first problem. Using the Hoffman apparatus for electrolysis, a chemist decomposes 36 grams of water into its gaseous elements. How many grams of hydrogen gas should she get? Theoretical yield. Okay, so our equation is water, right? H2O. And we're going to break it down into hydrogen gas, then oxygen gas. Is this balanced?
I have no idea. Yes. No.
No. We're going to need 2 of those. Cool. Now, when we do our BCA chart, we have to do it with moles and not grams. Oh, dang. So the first thing that we're going to need to do is figure out how many moles there are in 36 grams of water. So if we've got 36 grams of H2O, what does one mole of water weigh? Oxygen is 16, 18. So for 18 grams of water, we have 1 mole of water. So that means 36 grams of water is 2 moles. So here we've got 2 moles of water. What we want to know is how many grams of hydrogen gas we should get. How many, if we start with 0 moles, 0 moles. If we use the whole 2 moles, right, so that we have none left, how many moles of water how many moles of hydrogen should we get? 2. Because the coefficients are the same, so this number of moles is going to be the same. How many moles of oxygen should we get? 1. So, but it asks us how many grams of hydrogen should we get. So how many grams is 2 moles?
36. Wait, hydrogen 2. Right?
It's hydrogen gas, right?
No,
How?
sorry, four. I lost one.
You're wrong, Grant.
No, you guys are like just yelling out a bunch of different things. Do
It's
you,
four. It's four.
I need to tell you guys the story of Clever Hans. Okay, if we've got 2 moles of H2, right? 1 mole of H2 has a mass of 2 grams. So it's going to be 4 grams of H2. Okay, Clever Hans is this horse. And the story is that Clever Hans could do math problems, right? Because he's Clever Hans, he's smart horse. You know this one? And so the owner would go up to Hans and say things like, "What's 2 times 2?" And to show his answer, Hans would stomp his foot. Right? Only he would do it slower because he wasn't doing it for dramatic effect. But what would happen is Hans would sit there, he'd get these right every single time. Every time. And people were like, "This horse can't do math. That's crazy," right? So it turned out that what Hans was doing is he would watch his owner, and the owner would get really excited when Hans got to the right answer. So Hans had no idea what he was doing, except he knew that if he stomped his foot for a while, eventually his owner would get really happy about it. And then Hans would stop because the owner would give him a sugar cube when he was done. And so Hans had no idea what was going on. So when you guys are sitting there and you're all like, 1, 2, 4. Is it 3? Can it be? Is 3? Like, is that an option? You know, like, so I'm not, if I respond, like, it's not because I'm convinced that you guys are right? Because it could just be that you're just waiting for me to be like, yeah, that's the right answer. But you guys never do that, right?
No, never.
What is the first thing say? I have 2 questions. What is the first thing? What is the percent yield? Because I have most of that. I have the most of the percent yield question at the very top. Theoretically, thank you.
There you go. Yeah. So like one of the things that I learned very early on in high school, was that our Spanish teacher would make us talk in Spanish in class. And if we said like, I don't know the word for shoe, she would say to us, look it up, right? If we said el shoe instead, she would correct us. So we learned pretty quickly to not say, I don't know the right word, and just to make up a word. Because if we made it up, she would just tell us what the right word was. Yeah, el shuo. I don't know if I would have gone shuo.
Oh, definitely.
It would have been Shua.
Schwa.
Schwa.
Yeah. So like, you know, I try to not have tells because I actually want to know if you guys can understand it. But I think that you guys are catching on pretty quick.
I have another question.
Okay.
How did we know that hydrogen was 2 grams?
Because if you look at the periodic table, I just have it memorized. I know.
I know oxygen and hydrogen.
Did you just say sacred text?
That's all I know.
It depends on what part of the year I am, how good my recollection is. So your periodic table, if you guys need copies of these, I just like pull them off the test sometimes so you guys can have copies if you want. But for hydrogen, you see the number at the bottom. That's the mass of 1 mole of that atom. So it's 1. The ones that I know hydrogen, carbon is 12, nitrogen is 14, oxygen it's 15.99, but it's basically 16.
So I write 16 grams for oxygen.
Is it oxygen gas or oxygen?
Oxygen gas, right?
If it's oxygen gas, you're gonna need O2, so that's gonna be 32 grams per mole.
I also have a legitimate question. How do you measure? Like, how do they measure air?
What do you mean? How do they measure the mass of air, or how do they measure the volume of air?
The mass.
Okay, so do you remember we talked about standard temperature and pressure? STP. And so standard temperature and pressure is at 1 atmosphere, 1 liter of air. At 0 degrees Celsius, 1 liter of air has a pressure of 1 atmosphere. And so what they did is they said at those conditions, 1 liter of air is 1 mole. Because they didn't actually know how many molecules were in a mole, they decided that that was true first. And then they measured the mass of 1 liter of air.
Yeah, how? Like, did they
Put it in a balloon and like put it on a scale.
Put air on the scale.
And they calculated your weight.
You can weigh it.
They just grabbed all of their hands and they smushed it on the scale.
Put the air in.
And they calculated.
And then you subtract the mass of a balloon. If you take a balloon and you put air in it, and you have a balloon that has no air in it, you weigh it, like you actually get a different mass. It's very strange because it feels like that shouldn't work, but it does.
I'm so confused.
Are you skeptical? The other thing you could do is if you know that, if you know that that oxygen and hydrogen combine in a 2-to-1 ratio, then you could combine them, make water, and weigh the water. Yeah. And so that was the way you could check for a lot of those. Is you could take 2 gases, produce something that was either liquid or solid, and then weigh those things.
So do you weigh more when you suck in a lot of air and then hold your breath?
Theoretically, yeah.
Step on the scale?
You should. I mean, it's like the same thing as like if you drank a glass of water, do you weigh more? Like if there's more mass in your body, you should weigh more.
Well, that's why never mind. There's something I'm saying on here.
I get a cover now.
My socks said you made a very weird.
But that's a good question, though. I mean, people. You remember we did the Priestley thing, or we tried to do the Priestley thing online? Where you guys had the little like computer thing, and you'd like change. If it didn't work very well, and I got really frustrated because it didn't work. Yeah, there was like this online activity we tried to do where you actually like it's online, so it's like clicking on things. But the idea is that you combine different things together and get different products. And so what people could do is work out these ratios. Thank you. And then use that to figure out, what the ratios were, and then go backwards to sort out all this periodic table stuff. Early chemistry was kind of like the Wild West. It's like, well, we're going to try this and see what happens. And they actually figured out a lot of things without a lot of equipment, which I think is the most interesting part. Scheffler.
So for the second question, it is like liquid sodium chlorine gas. Is that Na or Na?
Liquid sodium, just Na. Yeah. Chlorine is diatomic. So most gases that we see, like that are made of a single element, that occur in our reactions are going to be diatomic. The ones that are monatomic don't like to react with things, and so they don't show up in the reactions. Struggle is real over there. All right, how much time we have? We have a few more minutes. Yeah, so what we're going to do tomorrow is I'm going to have you guys work on the percent yield thing. If you wanted to get a jump on that, you could start it now.
I don't think my brain could possibly handle it.
Well, that's the issue.
Yeah.
I'm going to have you do it tomorrow. I just wanted to show you today. Yes, ma'am.
So when you're filling out like the BCA chart, you can't use grams. You always have to convert it to moles.
Yeah, your BCA chart has to be moles because that's the unit that we can use to talk about ratios. Since every element and every molecule has a different amount of grams per mole, the ratios don't really work. Hey, Jack, do you have any questions?